Topic 6 is integral properties, and I'm going to show you a couple different examples. One without calculator, one with calculator. Typical non-calculator kind of a problem. So we're going to rewrite this as a single integral. First thing you should observe is whether these two functions are the same. If they're the same, then what I would have done is I would have changed this to a plus, make this go from 4 to 2, and see if I can combine it. And if I get something the same across diagonals, I can combine them. Right now, they're not the same functions. I can't even combine them. Okay, so what I need to do is recognize the fact they're both too wide. So I've got to shift one function so it matches the other. Well, one option is to shift the g of x. Now, after I do my shift, this term right here is either going to be x minus 2 or x plus 2. Just check to make sure it still follows what it originally was supposed to do, which is going from 2 to 4. If I plug in 6 into this equation, I get 6 minus 2 equals 4. So that worked. And if I plug in 4 into this equation, 4 minus 2 equals 2. That works. So that's what we need to have happen. So you just have to check it. But you check it afterwards. A lot of students get messed up because they try to do it beforehand. You first make your adjustment, and then you see if it matches the original, not if the original matched the new. That's where the mistake gets made. You could have also shifted the other direction, where I did it from 2 to 4. Notice that the f of x now goes from 4 to 6, and that's what it originally was supposed to do. Real typical kind of a problem is part B. You've got to break up the integral. So it's the integral from 2 to 5 of f of x plus the integral from 2 to 5 of 2. Well, they gave us this one. They told us this equaled 3, so I already know that one's 3. This is a rectangle. So you could do the antiderivative, 2x evaluated from 2 to 5, but I think it's easier just to realize it's a rectangle with a height of 2 and a base of 3. So we get 6 plus 3, that equals 9. Okay, for a calculator kind of a problem, or even non-calculator, you could possibly get this thing as a non-calculator one, is the application type of a problem. So we have a cyclist in a race, and the rate is shown to the right, which is in feet per minute, at various times. We want to use trapezoids to approximate the value of the integral from 0 to 60 of r of t. And then we have to interpret what this means in terms of the context of the cyclist. Well, trapezoids. What you need to do is we have to average these two values times the base. So we add these two together, divide by 2 times 10. Then I'm going to average these two values. This width right here is 15. My first base is 10. My next one's 15. And then 20. Average these two. Last one's going to be 15. Average these two right here to 4,000 and 1,500. And you can leave your expression just like that. Just showing the average, that's what they need to see. Now, if you do simplify it out, you're going to get 185,075 feet. Now, this is kind of a little bit of a dangerous thing. If you make a little arithmetic error, you could lose points. But you have to show your computation. If you went over and just gave the answer, you're not going to get any points at all. So that's really important. Now we've got to interpret the results of the cyclist. So if you did the original one, the first one, what we've got to realize is there's 3 components we have to have. This represents, when we add up the integral, it's getting the total of, and I got to figure out what my units, it's the total feet, because remember I have feet per minute times minutes, and the minutes will cancel. I get total feet traveled, and I got to specify on the time interval. So the integral shows the total number of feet traveled by the cyclist in the 60-minute time interval. 3 components: total, units, time interval. You have to have all 3. If you don't have all 3, they're not going to give you credit for it.